And to stay in keeping with Dan's tradition of doing these talks on either the birth or death anniversary of the individuals concerned, this is actually my birthday today.
Oh, really? Happy birthday.
Thank you.
Let's sing, everybody.
Yes,
Happy birthday to you. Happy birthday to you. Happy birthday, dear Mahadev. Happy birthday to you.
Thank you. That was lovely. You have a good singing voice there, Dan. This is good.
I can play the guitar.
Happy birthday, Mahadev.
Okay. Thank you. Oh, Bruce.
Yeah, my birthday was on Sunday.
Oh, wow. Look at that. I didn't realize we had such close birthdays. Fantastic.
Yeah.
So you have to do a presentation, Bruce. Can we go back to Sunday? I mean.
Yeah, you have to do one too, Bruce. I think you were planning to do one on Peter Rice and your experiences, right? That would be wonderful. Anyway, let me get going on this one. So again, also in keeping with Dan's previous presentations, I should maybe give you a little, very short history of myself. So I was born in Kenya, in the city of Nairobi, of Indian parents. They actually went from India, where they had both graduated and got their bachelor's degrees. And the British government was recruiting in all of their earlier colonies for school teachers to go and teach in schools in their newer colonies. And so my father happened to apply to that and be selected. So he went out there as a chemistry teacher, and then a year later married my mother, and she went out there as an English and art teacher. And I was born a couple of years later in 1957 in Nairobi, which at that time was still a British colony. So I had the first 8 years of my life in Nairobi in Kenya. I have relatively few memories of that period of time. Of course, some fleeting ones, but nothing very significant. My more significant memories are when my parents then moved to the country of Zambia, which is further south in Africa, to a very small town called Kabwe, which was literally in the middle of the country and in the middle of nowhere. And there were school teachers there, and that's where I then spent the formative years of my youth, from the ages of 8 to 16. The interesting thing, though, about that location was that Zambia in 1965, which is when we moved there, had just got independence, but the school systems and so on were still heavily dominated by British influence. And so in my school, about half of our teachers were actually British. The other half were a mixture of South Africans, Indians. At that time, no locals, I'm sorry to say. By the time my sister graduated from high school there 3 years later, there were some Zambian teachers, which was a good thing. But in my time, they were not there. So I was there till the age of 16. And at that time, we actually ran out of education options because the university in Zambia was just getting going. And so my parents and I discussed it, and they decided to send me to England for further studies. So at the age of 16, I went to a boarding school in England for 2 years to finish my high school. And then from then on, went to the University of Durham, which is in the north of England, to study engineering. And I was there till 1978. And by the time I graduated in 1978, my parents had decided that it was time for them to move out of Zambia, because by then conditions in Zambia had changed a lot, and the security situation was bad. And I think the turning point was when my mother was in the house alone, and the house got broken into in broad daylight. And so that fortunately she was not hurt or attacked in any way, but that pretty much made them decide that the time was up to leave. So as I graduated, my parents arrived in England as well, and all of us went to a very small apartment in London, and we were all looking for jobs. So that's my mother, my father, and myself, all looking for jobs at the same time in the summer of 1978. My sister at that time had just finished her high school, and she was going to join university in London, which is why we chose London as the place to be. And as it would happen, I saw a very small ad, literally 2 lines, that said, Varup and Partners is looking for mechanical and electrical engineers to join their building engineering division. Now, at that time, there was no internet or anything like that. And my engineering course was not particularly focused on the building industry. It was a very general and broad-based engineering course. So firstly, I didn't know anything about Varup. I had no idea what building engineering was. All I knew was that I was a mechanical engineer and they were looking for mechanical engineers. So I applied. I went for an interview with a very fine gentleman who now retired called Keith Dawson, who grilled me for an hour. And we spoke about all sorts of topics, things I was interested in, like mountaineering and photography and so on. Our conversation didn't veer much into technical subjects. At the end of that interview, Keith Dawson said to me, "You really don't know anything about building design, do you?" And I had to answer truthfully. I said, "You're right. I know nothing about building design." Uh, but to cut a long story short, he sent me off to do some research on it and come back to him in a week, which I did. And maybe I sounded a little more intelligent at that time because he actually gave me a job. And I've stayed with the company ever since. So from September, actually it was September 11th, 9/11 in 1978, when I joined Arup. And I worked there till I retired in March of this year. But my connection, sorry, not this year, of 2020. But my connection with the company remains because during that time, or towards the end of that time, I got put on the trustee board, which is a board of 9 individuals, 5 of whom are retired members of the firm, and 4 of them are current directors of the firm. And we provide a kind of governance body for the company. We appoint the members of the main board, and we make a few other key appointments within the company. And we review the board to make sure that its actions and so on remain in conformance with the culture of the firm, which was established by Sir Varup in, I think it was 1976 or thereabouts. He gave a speech called the Key Speech, which we call the Key Speech, which you can search and find on the website and so on, which really is like a manifesto and a statement of what this firm ought to be about. Um, what is very important to me personally about the Key Speech is that, again, when I joined the company, I had no idea this thing existed. These days, when anybody joins, firstly, they would have done their research on the internet, and secondly, our HR people are very good at shoving this down people's throats. But when I joined, that didn't exist. And so I had no idea that there was such a thing as a key speech, and it set down the principles, etc. About 8 or 9 years into working there, I came across this document. And when I read it, the power of it was that I recognized the place that I'd been working in for 7 or 8 years in the words that were in that document. And so that really reinforced it as really the basis of our culture. And I would say that Arup, sorry, not to do too much of a PR on Arup here, but the firm does have a very unique culture. It does not have human shareholders that own the company and get the profits. The profit is shared through all the staff, whether you happen to be somebody working in the mailroom or the director of the main board, you all get a share of the profit of the firm. And it's also a global profit. So it's the collected profit from around the world that is then shared out. It is not based on individual performance or how well your group did or what work you personally were successful in doing. It's a very kind of equal and leveling thing. So if one part of the world is doing well and another part of the world is having difficulties, everybody still gets a profit share. And you can see those economic cycles move around the world. Certainly, if you've been around for as long as I have, and it's a very good sharing environment. And it also means that people are very open about pulling in expertise from other places and other offices, other countries even quite often, when they have some issue that they need to resolve on a project that they don't have local expertise in. So it's been a wonderful place to work. I cannot compare it to other places because I've never worked anywhere else. But what I can say is that people that join us from other companies are generally very favorably inclined towards the culture and the environment that Arup and his early partners managed to create within the firm. So I think that's enough about that in terms of history. Or maybe I should go to the present. So I now live in okay, having worked for Arup, I joined them in London. I worked there till 1992. And in 1992, there was an opportunity to come to New York to set up the mechanical and electrical side of our operation here. At that time, we had only about a dozen people in New York. The office is now the biggest in the US with about 500 people. But in 1992, we were a dozen people. I was the first mechanical engineer. And it was an exciting time. I initially came for a 3-year assignment and then decided that this was exciting here, full of opportunities, and I stayed. Along the way, I got married as well. I have 3 children, 3 boys, and we all live in a house in New Jersey that's near the Princeton University campus, about 10 miles from the campus, which is very convenient because along the way also, maybe about, nearly 20 years ago, I got appointed as a visiting lecturer at Princeton University, and I've been teaching a couple of courses there to architecture students ever since. And despite being very busy at work, I always protected that part of my activity to make sure that I fulfilled my teaching commitments because I think it's an important way of giving back. And it is also something that gives me enormous joy. So, and I continue to teach at Princeton despite having retired from project work at Arup. Okay, so enough about me and history. Let's jump straight into the environment. So this is an image that I suspect that most of you have not seen before. All of these spheres that you see on here are to scale. And let me explain what they are. So obviously you see the spheres that represent the Earth. And the Earth has a diameter of 7,900 miles, which is 12,700 kilometers. So to scale, those 2 large spheres of the Earth are 12,700 kilometers. Now on the on the right-hand side, you see a pinkish sphere superimposed on the Earth. That is the sphere of all of the atmosphere around the Earth that's collected together in one ball. Now, we seem to think of the atmosphere as something vast because it covers the entire surface. But what we need to be aware of is that it's actually a very, very thin layer of air that covers the surface. And when you pull it together, it forms this sphere, which is only 1,200 miles or 1,900 kilometers in diameter. And relative to the scale of the Earth, you can see how small it looks. Now, on the left-hand side, you have that translucent blue sphere, which has a diameter of 860 miles and or 1,400 kilometers. And that is all of the water on the Earth's surface, the seawater and the fresh water collected together into one ball. And again, we think of the oceans as vast because they cover, I don't know, more than the land surface. The number is somewhere around 2/3 or something of the Earth's surface is covered in ocean. But again, even though some parts of that ocean are miles deep, when you put it all together, there's a relatively small amount of material, which forms, again, a thin layer that covers the surface of this sphere that we call our home, the Earth. And it's only 1,400 kilometers in diameter. Then between the 2 spheres of the Earth, you see 3 smaller spheres. The blue sphere on the left, the largest of those 3 small ones, is actually the fresh water that's available on the Earth. That's all of the fresh water. And that is 250 miles or 400 kilometers in diameter, if you put it all together as a sphere. The little green sphere is the water that's actually available for humanity to make use of. and that is 40 miles or 65 kilometers in diameter. The thing about those two freshwater spheres is that they are somewhat renewable in that basically you get evaporation, rainfall, and so on. And so they kind of cycle around. They're not fixed entities. But I don't know if you noticed that little red dot. Can everyone see the little red dot? I'm pointing at it now with my cursor.
Yes.
That little red dot is a sphere of 12.5 miles or 20 kilometers in diameter. That represents the full sum total of all of the fossil fuels that we know exist on this earth. So the oil, the gas, the coal, that's how much of it there is. And the main environmental challenge that we face now is that we're digging out this material from the Earth's surface, and then we are burning it in various ways, consuming it in various ways, and the carbon dioxide that's released by that is coming and polluting this little sphere over here, which is the atmosphere. Now, when you look at it in this way, this debunks the idea that our environment is so huge that a little bit of pollution over here can't really do that much harm. Now, that used to be maybe 100 years ago, very much the view that the environment is so vast that you can put pollution into it and it will just absorb it. But when you look at it in this way, you actually see that, in fact, it's not that vast. The things that are being polluted, like the oceans and the atmosphere, are relatively small in scale. And so it is very visible in this way that human activity can lead to those very fragile environments actually being damaged. So I put this slide up at the start of these lectures just to sort of give us a sense of scale and a sense of immediacy to the problems that we are facing as humanity as a result mostly of our own actions in the past, however well-intentioned. And one of the key challenges, certainly now, is the level of carbon dioxide in the environment. The latest reading is 417 parts per million from February the 11th. And down below, this graph actually shows you the carbon dioxide measured over the last month. And you can see even in that 30-day period, we've gone from readings around 415 up to 417. So there's a steady march of carbon dioxide in the atmosphere, which is primarily as a result of the burning of fossil fuels or the consumption of fossil fuels and the release of the carbon dioxide that was essentially sequestered by those fossil fuels. And what do I mean by that? Well, again, going back to geological time, there was a time when, in fact, there was very little oxygen, maybe even no oxygen in the Earth's atmosphere. And all of that was the space that's currently occupied by the oxygen was basically carbon dioxide. And all of the oxygen that we currently have in the atmosphere is not occurring just in of itself, but is the result of photosynthesis over billions, in fact, of years, at least let's see, about 1.5 billion years of photosynthesis that has been taking place, where basically that carbon dioxide has been used up by plants and oxygen has been released as a product of that photosynthesis that is built up in the environment. And a lot of that carbon dioxide got converted over time into the fossil fuels that and other things, but the fossil fuels that we currently use. So trees and woody material got compressed and heated to form coal. Various sea creatures were the source for oil. And there are multiple sources for natural gas, both due to both land-based and aquatic. And so all of those fossil fuels are essentially the product of the biosphere of life on Earth. And when we burn them, what we're doing is we're taking that carbon dioxide that was sequestered over a long period of time and releasing it into the atmosphere in a relatively short period of time. And so obviously there is quite a lot of carbon sequestered here and there, not all of it in fossil fuels, but what has happened over time is that our current climate and life on Earth has adjusted to a level of carbon dioxide of around 250 parts per million. And we have grown that basically over my lifetime. So my lifetime is more or less coincident with the measurement of data from the Mauna Loa Observatory, which started in 1958. So if you look at this curve, this part from 1958 onwards is the measurements at that observatory, and they take hourly measurements, and they've been keeping a rigorous record. If you look at that starting point, it was just around just over 300 parts per million. And over my lifetime, that has already gone up to the 417 that we see today. Now, how do we know about CO2 levels way back in history when measurements were not being taken? Well, this is where Antarctic ice cores come to play. So basically, when you get snow falling in the Antarctic, it traps bubbles of air inside the snow, and then it gets compressed. And so if you take an ice core, dig deep into the ice and pull out a core, you can see rings that are pretty much like the rings on a tree going back in time. And so people have been able to extract the gas bubbles and analyze them to see, well, what was going on in the atmosphere. And you can see prior to about 1750 or so, the carbon dioxide level was sub 300. It was around 200, what's it, 275, 280 parts per million. And in fact, there are graphs that you can see on the Mauna Loa site that will give you data going way back in time that shows that there were fluctuations, but the fluctuations are all averaging around this 250, going back as long as that record exists. And then things started happening basically related to human beings that started around the 1500s. So in the 1500s, the availability of wood in certain places like the United Kingdom and so on started becoming difficult because there was a lot of deforestation, and people needed alternative sources of fuel. And so coal was something that had been known for a while. It started getting into widespread use for domestic heating and so on around the 1500s. And that didn't have much of an impact in the environmental carbon dioxide level because it was actually a very small scale level of emission. But then what happened in 1776 was that James Watt perfected the steam engine. Up to that time, steam engines had existed, but they were relatively low power and very inefficient in their use of fuel. But James Watt made certain innovations that actually made them now very practical and feasible and economic means of generating work. Now, up to the arrival of engines, if you wanted to do any work, it was either manpower or it was animal power that was used to get things done. With the advent of the steam engine, we now had, there was water power as well. So there were windmills and mills that made use of either water or wind as a means of generating power. So I shouldn't forget that they existed as well, but they were not particularly flexible, and they were usually single use, that often just for pumping water or for grinding grain. With the advent of the steam engine, in around 1776, 1780, that started taking off. And you do see, in fact, an uptick in the carbon dioxide in the environment that happens in that period. The next innovation to pay attention to was that, again, oil was discovered sometime in the 1700s, but the first modern style oil well for commercial exploitation was established in Titusville, Pennsylvania in 1859. So from 1859 onwards, you have the era of oil, and you see there a steady rise in the carbon dioxide level as a result of oil coming into use. then another landmark along the way, and by the way, this is not a comprehensive timeline. I've just picked certain key dates that kind of establish human emissions of carbon dioxide along the way. So in the 1880s, you get Edison and Westinghouse in the United States competing for establishing electrical technology and establishing standards in terms of electricity. Edison was a direct current guy, and Westinghouse preferred alternating current. Westinghouse won that particular argument, and electrification really started in earnest around the beginning of the 20th century. And with electrification, we got things like air conditioning coming in, and much of the electricity, certainly in the early days, was generated from fossil fuels. And so the increasing use of electricity for its versatility and convenience and its ability to do things like cooling started to increase the energy consumption in the building stock. And that is a process that continued. And the final landmark that I have on here is 1908, which was the introduction of the Model T Ford, which actually brought transportation, again, fossil fuel based, into public use. It's interesting that before that era, in the late 1800s, you had a combination of there were some very early steam-powered cars that were obviously not very flexible. There were some electrical vehicles. So Studebaker in the late 19th century was offering vehicles that you could get either with a gasoline engine or with a battery and electric motor, which was quite interesting. But the thing is that because of the size of battery required to go long distances, electric vehicles just fell out of use at that time, and gasoline just took over, and diesel as well, as the means that powered the transportation explosion that then happened after the Model T Ford and other vehicles came on the market. And so that then brings us pretty much to the present age. So if you look at what has caused the growth in carbon dioxide emissions over time, it is the fact that all of these technologies that were developed at the beginning of the last century have become more ubiquitous. They've become more energy consuming. They've become more widespread around the world. So from being something that was there only in a handful of countries and only in cities, you can now go to any corner and find the use of fossil fuel consuming vehicles, etc. And so that brings us then to, let's just look a little bit at where we are. This data is a little bit out of date. It's from 2007, but it more or less holds true today in terms of the relative proportions of carbon dioxide. And forgive me, I can't cover the entire globe with these lectures, so I'm going to focus somewhat on the situation in the United States. But it isn't dissimilar in most parts of the developed world. And indeed, in places like China, which are developing very fast, they are also getting closer to this kind of level of emission in terms of where it comes from. So you can see that about a third of emissions are due to transportation. And what the transportation sector is doing about that is really trying to increase the electrification of the fleet, and also to some extent making use of other alternative fuels like hydrogen or methane, which also is a fossil fuel that emits carbon dioxide, but to a much lower extent than gasoline and diesel. What always surprised me is that the industrial emissions actually represent less than a third of CO2 emissions. I always thought that industry was the thing. And if you want a poster child for carbon emissions, you'll see a picture of a factory with a chimney belching smoke. But in fact, that only represents 27%. In fact, it's closer to a quarter than a third of emissions. The big one here is really buildings. So nearly 40% of emissions come from buildings, and of that, half of them are residential buildings. and the other half are commercial buildings. So you can see that certainly in a lecture like this, which is mainly aimed at architects and other professionals that are in the building industry, we as an industry are actually responsible for a third to 40% of emissions, certainly in developed countries and increasingly in other parts of the world as well. And so the building industry really must play a pivotal role in achieving carbon reductions. So coming back to my own history with regard to this, at the time when I joined Arup, there was no real understanding of carbon emissions and carbon dioxide in the atmosphere as being an issue. What was the issue of the day was that in the mid 70s, the OPEC countries had clubbed together. In fact, they formed OPEC at that time, and they decided that oil was being exploited from their countries and being sold at way too low a price, and they were not getting enough of a return on that resource. And so they unilaterally clubbed together and raised the price of oil. And there were two oil price shocks that took place. I think they were 1975 and 1978 or 79. I'm not sure of the exact dates, but they were in that 70s period, during which time the price of oil was just increased by quite a high amount. And of course, the Western economies that had become somewhat dependent on oil as a feedstock and fuel source were immediately impacted by that. And so there was a dramatic thrust across the entire economy to try and cut down on the consumption of oil and to find alternative fuel sources to put in its place. And so I started my professional work as a mechanical engineer at a time when energy conservation was the name of the game. And I was involved in projects like this one. This is a what you might call well, it's called in the UK council housing, but it's government provided housing for people. Therefore, it's no frills really. Obviously, it has to meet minimum standards, but the government doesn't want to spend too much on these. And the plan here was to actually try and reduce the energy consumption of these buildings. At that time, a lot of domestic heating had actually transitioned to oil. And so the idea was to do the heating for these buildings not using oil. And what did we decide to do? Well, since coal was a product of the UK, it was relatively cheap and plentiful. It would last a long time. We said, oh, why don't we make this coal powered? Now, that decision today would be absolutely slammed because of the carbon emissions that would result from coal burning, certainly, and the pollution that it would cause within close by burning it in close proximity to houses would just be unacceptable. But at that time, it was thought of as a good idea to transition from oil to coal. And so all of these houses were designed to make use of this central coal plant. But the houses themselves, also a lot of thought went into making them passive solar and to minimize their energy consumption. So you'll notice that they're all oriented in a specific way. And the study then showed that you could go with it. So they're all south facing essentially. But to make that not too monotonous, we did work that showed that you could move about 20 to 25 degrees off due south without affecting the performance too much. So these long facades of these blocks all face within 22 degrees either way of due south. So the south-facing facade is maximized. The back of the houses was actually a single story. It was two-story in the front. And that was because we could really insulate these roofs to have a very low heat loss. And we minimized the north facade of the building, which doesn't get any sun and is therefore loses more energy. So there's a lot put into minimizing the energy consumption. But there were also some decisions that were made that were, I think, not ones that we would accept today. So for example, we had meetings on figuring out how we could prevent the occupants from raising the temperature of their bedrooms above 18 degrees Celsius so as to conserve energy. So this is like Big Brother deciding that they shouldn't have a warm bedroom or warmer than 18, and trying to put measures in place to prevent that, which looking back on it was a horrific thing to do. We would not do that kind of thing today. So these days there's a much more holistic view of matters of energy consumption and environment, where we try and address social issues, economic issues, as well as environmental issues all together to get holistic solutions. We don't often succeed in doing that really rigorously, but definitely the aim is there these days amongst modern practitioners. So also around this time in the late 70s and early 80s, computer technology started coming into the design field. So prior to this, most calculations were done by hand using maybe rudimentary mechanical calculators. But to actually have computer programs that you could use to calculate annual energy use, and to do modeling on how do you modify your design to actually improve the energy performance, those things only started to come in around the late 70s, early 80s. And this housing project was one where we actually used some very early rudimentary energy programs to try and figure out the energy flows that would take place in a holistic way. So you can see here, this diagram actually shows the power station, the boiler house that we have, and the dwellings to show where the energy is actually going through. And that actually was the start of a bit of a revolution in terms of energy technology in buildings. So by the time you get to the Lloyd's building, and now we're looking at a design that happened in the early 80s, the thought that buildings ought to be designed to conserve energy was becoming quite widespread. The Richard Rogers partnership embraced that, and they were working at that time with one of my directors and mentors, a guy called Tom Barker, who actually they got to know while doing the Pompidou Center in Paris. So Tom Barker had become their go-to mechanical engineer. And in the early competition designs for this, they decided that saving energy was going to be a key function of this building. Now, this was a project which was in some ways a dream project for any architect, because the client didn't really have a limit on the budget that they could put into the building. They didn't impose any limit. And so basically the architects and engineers went to town. The structural engineers did some very exciting things that I'm sure Bruce can tell us about at some point. But I'm going to focus on the environmental measures that we put into this building to save energy. So one of the things is that you may notice if you look at these interior pictures that there are some devices on the floor in various places. So it was decided that we would do what's called a displacement ventilation system for this building, where the air is supplied from the floor. At that time, it was very novel. These days, it's fairly common, and most of you have probably come across such a system. But the idea is that you condition the lower occupied layer where the people are in, the lower 2 meters, and then you allow the temperature above their heads to rise up to whatever it gets to. And usually by the time you get, if you have 21 degrees as a comfortable temperature in the occupied zone, near the ceiling, it could be as high as 28 or 29 degrees, but there's nobody there, so we don't care. Other things that were done, so having supplied the air to the space, you see these light fixtures that were actually not merely light fixtures, but also a means of collecting the air from the space. So the space that was supplied would then be cycled through the lights. And in doing so, it would pick up a lot of the heat from the light fixtures. About 50% of the energy in these light fixtures was converted to heat that would be picked up by that airstream. That would make it even warmer. So if it was 28 there, it may get up to about 30 degrees by the time it goes through the light fixture. The next stop along the way is that the air from these fixtures was then passed down between 2 of the 3 layers of the exterior facade, thereby providing an actual means of using waste heat to deal with the heating demand on the exterior facade. And then from there, that air would cycle back to the air handling units that were located in these towers. And you can see the ducts coming down. So of the two major ducts, one is a supply duct that's supplying the air to the floor space, and the other is a return duct that's picking up the air from the facade and taking it back up to the top. In addition to this, we had means of taking the waste heat that was generated during the day and storing it in the sprinkler tanks and bringing that heat back out at the start of the next day to help heat up the building. We had a lot of exposed thermal mass. You can see that all of this structure at the ceiling is exposed to the space, and underneath this floor, the structure is exposed to the supply air that's coming in. And the thermal mass of the building itself was leveraged to moderate the conditions inside the building. And it was a fairly successful scheme. And I was the young engineer who was familiar with computers at that time, who was set the task of doing a lot of the modeling here and basically doing the energy modeling for the building. And I must say that that ended up being a very disheartening process for me, because what I discovered was that in the process of designing these exterior towers, and there are 6 of them that sit outside the main plan of the building, the architects, in order to express whatever it is they were trying to express as part of the high-tech movement, created a lot of extra surface area. So you see that this staircase is actually a spiral. So any part of this staircase has 4 exposed surfaces. It has an exposed floor, an exposed roof, 2 exposed walls. And by the time you add up all of that surface area, and also the toilets, so these toilets were pre-manufactured off-site and then brought in and plugged into the building as finished elements. Each of those also has exposed surfaces, 5 exposed surfaces.
Please be kind and turn off the microphones, with the exception of Mahadev. Thank you.
And anyone who wants to interrupt and ask a question, that's also okay. But otherwise, yes, please mute your microphones. So there was so much surface area on this that when I did the energy calculations, I found that these towers, which were essentially toilets and stairs and service shafts, were consuming almost as much energy as the main building itself. And so we were bending over backwards to develop technological solutions to reduce the energy consumption of the buildings, and then throwing it away by creating gratuitous surface area in these external towers. Now, looking back on it, I still love the project, but at the time, as a young engineer, very idealistic, I felt that this was highly irrational and irregular. My bosses did not want to hear it from me. And so I actually left to do a master's degree. That was my excuse to escape from this project and to go and do something else that I always wanted to do. I joined Arup with a bachelor's degree. I felt I was undereducated, so I went for a year to do a master's degree with the sponsored partly by Arup, for which I remain forever grateful. And then I returned to the firm after a year, by which time, obviously, the project had moved on and been handed to other people. But it's interesting that we can have very good intentions in terms of energy. And the target for this building was something like 250 kilowatt hours per square meter per year as an energy consumption. Today, a low energy building would not be proud of such a target. We would be looking more for something in the 100 to 150 kilowatt hours per square meter per year in that type of climatic zone, maybe even as low as 75 or 80. But at that time, that was considered to be a very worthwhile target, which we actually met. But thinking about all of these surface area issues and so on, had we thought a little more carefully about what the architecture was doing to the energy consumption, we might have done much better. So again, in the mid-80s, the idea that buildings ought to save energy and that the windows ought to be shaded and all that kind of thing was becoming quite widespread. Certainly in the UK, it was. And then here's a commercial building that has since been demolished. So it shows you how old I feel. The buildings I worked on have been demolished. This is Ropemaker Place. And on the left-hand side, I show this picture because the facade there is in full sun with all of these shading devices, and you don't see any shadows cast on the facade. So essentially, these shading devices went from having an actual function to being some kind of decoration that certain architects would apply without necessarily looking to see whether they were doing anything meaningful. That wasn't, and of course they were applied on the south face as well, but there was no reason for them to be applied on faces where there was no solar radiation that needed to be dealt with. At the same time, we did some very interesting things with the atrium in this building. Atriums were also becoming popular. Quite often the approach was to sort of air condition the bejesus out of them, forgive my language, and people would pump lots of air, and we decided that was crazy. So what we did here was to put a radiant heating system in the floor of the atrium, which is the only part of the atrium that was occupied, and then allow natural ventilation to do the rest of the temperature control in there, on the basis that it doesn't need to be comfortable anywhere above head height. As long as there's ventilation that's preventing overheating of any of the elements, that should be fine. And that also worked quite well. I should point out that that was only feasible as a system because in parallel with computers coming into the workplace, electronic control systems were coming into the field of mechanical engineering. And you could have thermostats and actuators and other devices that you could program to respond in a particular way when a particular temperature or humidity was reached, and to open windows automatically. Things like that were not possible even 2 decades prior to that, but became quite mature very quickly as technologies that we could put into buildings. And that increased prevalence of advanced control systems was a key factor in actually allowing us to start saving energy in buildings. So I go then to now we're in the late 80s. This is another project with the Richard Rogers Partnership, as it was known then. It's now called Rogers Stirk Harbor. And this was a project where the partners actually left it to a couple of more junior individuals, one of whom was Ivan Harbour, whose name is now on the name of the firm. But at that time, he was not even a partner level architect, but he was one of the key architects on this. And I very much enjoyed my collaboration working with him and the other architects at Richard Rogers on this project. By the time we get to this stage, we're talking about late 80s, most countries had national energy codes that basically imposed certain energy criteria on buildings. So since we had the ability to model energy consumption, you could actually put down regulations that say you can't use more than X, or individual elements should have a particular minimum level of performance, etc. And all of that was in play on this project, which is in Strasbourg, France. Sorry, it says that at the top. You can all read it. And so we went into this project looking for opportunities to actually do better than the code. At the end of the day, we only just met the code for a very specific reason, which is that this front part of the building actually has the courtrooms. There are 2 courtrooms that are like drums. They're elevated above grade, and below them is a single glazed curved glass entrance hall. Now, the architects were adamant that the glass should be curved so that it is actually a circular entrance hall and is not made of facets. They did not want facets. And at that time, you could not get curved double glazing. You can do it now. So you can actually have insulated glazing that has 2 panes with an air gap and so on. It couldn't be done at that time. So it had to be single glass. And what we found as a result was that this head part of the building consumed more energy than the code would allow. So what we had to do was to make sure that the back of the building consumed less than the code would allow, so that the 2 would balance out. And that became one of one of the driving forces, if you like, for the later design of what came along. And there were a lot of very interesting features that were built into this building. So for example, if you look at these office wings, there are two office wings like this that go off the back of the building. They're made of concrete, and inside the offices, there's a lot of exposed concrete to leverage the thermal mass in that area. If you look at the climatic conditions in Strasbourg, it shows that there are relatively few hot days. And if you've done a good job with your thermal mass, you can actually avoid going towards mechanical cooling throughout the year. And so that's what we started off doing. So we had the exposed thermal mass. We had these exterior shades on the facade, which would come down automatically when the sun was shining on the facade. And of course, so as to not be draconian, there was an individual override in each office that would be reset at the end of every day, where if a particular individual wanted the sun to come in and defeat the shading, automatic shading, they actually had the ability to do that. But typically the shades would come down based on a time clock that would make sure that whenever the facade was in sun, the shades were deployed. The shades were such that they would let diffuse daylight into the office space, but they would exclude the hot direct sun. Also along this facade, there were these planter boxes that were irrigated, and the transpiration from those plants would help to cool down that element, which then also created a cold thermal mass at the perimeter of each office. And of course, the windows were operable, and natural ventilation was used to condition it. So a lot of study done to make sure that these would function appropriately. When it came to these courtrooms at the front of the building, they obviously needed heating and cooling. And we discovered that there was an aquifer that ran underground here that several buildings were tapping into as a source of heating and cooling. So it ran at a temperature of something like 16 degrees Celsius throughout the year. And by running it through a heat pump, you could extract heat from it for use in the winter, and you could use it as a means of rejecting the heat from your building in the summertime. And so that was a technology we deployed there. It's now relatively commonplace. So you can get a water source heat pump or a groundwater source heat pump for use in even domestic applications. At that time, it was somewhat rare, but it was deployed as a means of essentially reducing energy consumption, because using a heat pump scheme for doing your heating and cooling provides dramatic reductions in electricity consumption. So that was all done. The story takes a bit of a twist at that point, because we did the design, we handed the project over to some local engineers that was supposed to take it and see it through construction. And all of that happened around the same time as the collapse of the Berlin Wall. And with the Berlin Wall coming down, the Council of Europe, which was the client for this building, decided that this facility was not necessarily going to be big enough for their future needs, that they envisioned various other countries from Eastern Europe joining the institution, and so they would need more space. And so they halted construction. And at that time, the foundations had been put in the ground, but nothing else had been constructed. And they said, look, we need a bigger building. And I was not involved in that design process then. In fact, the structural engineer who was leading the structural design, a guy called Richard Howe, had left to come to Los Angeles. So he was in Los Angeles, I was in New York, and a brand new design team took on the challenge of increasing the size of this building while making use of the same foundations with minimum modification. Now, just the way I said that would lead you to conclude that therefore, whatever was put on this building to increase its size would be very, very light in weight. And that's essentially what happened. You can even see it visually here. That top layer that goes all the way around the building is very, very light compared to the heavier concrete construction down below. And then these drums were increased in diameter to accommodate additional judges, etc. Now, the problem though with making this part of the building light is that that part of the building was never designed with air conditioning in mind. And the new design team failed to realize that all that thermal mass was really an essential part of the environmental system as well. It wasn't just structure. And so they just extended the systems, but used the same type of systems in those spaces. And when this building opened, it opened in August on what might have been the hottest day of the year. And all of these top level offices were overheating. And guess where the most important people in the building had their offices allocated? It was in that top level. So that was really a little bit of a disaster. And I present it as a cautionary story because as you integrate design to the extent where the disciplines are interacting with each other and you're developing combined solutions, it's important for that knowledge to be kept active throughout the design process and into construction so that you actually achieve what was envisioned in the early part of the design. If you get a disconnect, as you do here, then you can do something in good faith and then find that you've actually ignored a very important factor, which was that thermal mass was a critical element in creating comfortable environments in this office. And that was just not even thought about until the building opened. And then, of course, they had to quickly go in and put in interventions to try and provide some cooling in that space. But frankly, it was an embarrassment. And had the original design team been involved all the way through, that could have been taken into account. But that was not possible because we had scattered to the four winds and there was no practical way of really engaging us. But I do present it as it's very, very nice to have creative ideas and integrated ideas and cutting edge ideas in the design stage. Making sure that the thinking gets carried through into construction is a whole other challenge. And there are several stories I will tell along the way that that have similar messages applied to them. So this is now moving to Kansai Airport in Osaka Bay. It's a Renzo Piano project where I was involved right from the competition stage through to the early part of design development in developing the design of this building. What is interesting about this is that the concept for the shape of this roof actually came from Tom Barker as a mechanical engineer. So while they were brainstorming a response to the competition brief, he suggested, why don't we use the trajectory of a jet of air across space, which if the jet is at a cooler temperature than the ambient air, will actually form a curved trajectory, which you can calculate. He said, why don't we use that as the form giver for the roof? And Renzo liked the idea. And that was then adopted as the means of generating the geometry. And so we tried various temperature combinations and velocities of air and so on to generate different curves. And Renzo picked one that he liked, which was then used as the means of creating the geometry for this part of the building. But then we had to make sense of this whole air jet system. And so we figured out that you could use that jet of air in reality to deliver the fresh air to this environment, but not to do much of the conditioning. And then you'd actually condition the space with these lower level air supplies that would, again, create a comfortable environment for occupants within 2 meters of the floor, but not try and condition the entire big volume of the space. So that turned out to be quite a good strategy from an energy conservation standpoint. But again, to demonstrate the importance of computers in all of this, by the time we did this project, which was getting towards the late 80s, we actually had the means of modeling airflows using computers. And this was a technology that we borrowed, in fact, from the aerospace industry, where they had developed this to a higher level. And we figured out that we could modify it for use in buildings. So this was one of the first buildings where this was used actually to validate a concept. But of course, the client was not happy to base such a big investment and a design direction on nothing but untested computer technology. And so we also carried out a series of mock-up measurements. And in order for a thermal mock-up that's modeling airflow and energy and temperature exchanges appropriately, you can't use a very small model. The model has to be at the smallest it can be is 1 to 15. And so we actually, in a warehouse, constructed a 1 to 15 scale model of a segment of this airport terminal. And here's a diagrammatic that shows that segment. And then we modeled the airflow and the temperatures and the heat gain through to solar and so on in there experimentally, and showed that the results that we were getting from our computer analysis was correlated pretty well with the measurements we were making from the model. And that then allowed us to use the computer technique to further refine and expand the design here. One tragedy that happened, it's a design tragedy, it's not a sort of human tragedy, that happened as a result of the value engineering, if you like, on this project, is that the Japanese government at some point decided that the project was costing too much, and they needed to shave some cost out of the building, and it was a mandate that we had to do it. And given the situation in Japan, you couldn't push back on that. You just had to do something. And so what was sacrificed were the skylights. So above each of these structural ribs would have been a linear skylight that was in fact originally designed to meet the lighting needs of the building whenever it was daylight. So you would never have to turn on the electrical lights during daylight hours. It was a very cool design of a skylight. And the structure down below would be kind of accentuated by the light shining through from these skylights. But it was the one element that could be eliminated without unraveling the rest of the design. Everything else was very interwoven, like these air ducts here. It's called an open air duct. It provides a surface for the air from this jet to attach to. And it helps to convey that air all the way across to the other side of the building. It's also a reflector for the electric lighting. So the lights are down below and they shine up onto it to spread out across the space. It's also an acoustic absorber. It also has some thermal insulating properties. So it is a multifunctional setup. You can't mess with it. So they decided to mess with the skylights instead, which obviously increased the energy consumption of the facility dramatically, and also visually made that a dark, electrically lit space rather than a daylit space.
And Mahadev, wasn't the original design full of planting as well that was value engineered? Wasn't it super lush, the original renderings?
It was also super lush. And in fact, if I may go backwards, this part, which is called the canyon, was really like a park. That's where much of that vegetation and lushness existed, and that also was, you're quite right.
Maybe that was a missed opportunity for the quality of the climate in the space.
Indeed. And the quality of the climate has two factors. It's the things you can measure, but it's also the psychological factors, how people feel in a space. And you feel obviously much better in a space with a lot of natural vegetation in daylight than you do in a space that's entirely sterile and made of man-made materials. That's my personal experience, and I'm sure it's shared by a lot of other people. Yeah, thank you, Bruce, for that. So I'm going to jump now to a whole different era. So we're now in New York. At this point, we're getting towards the end of the 90s. In fact, I think the master planning work that we did for the United Nations is around the year 2000. So Arup was appointed as the lead consultant to actually go over this entire facility, the United Nations campus in New York City, and do an evaluation and then come up with a master plan for the renovation of all of these buildings. And the idea was that we would create such energy savings by doing this, that the energy savings over a period of time, the time horizon was 25 years. The energy savings over 25 years would pay for the renovations that would be needed to the facility. That was the premise. And in fact, we showed that it was actually feasible. And the reason for that was that if you look at your typical buildings on this campus, they were extremely well designed, by the way. There was nothing wrong with the design thinking that went into these buildings. These vertical facades, the north and south facades on the Secretariat building that go up 36 stories, we surveyed them and they were like 3/8 of an inch out of vertical over that entire height. That's how precisely this thing was built. We opened up parts of this curtain wall and we found that the fittings were like the day they were installed. They had not degraded, they're not corroded, and there was clearly further life left in this building. And one of the studies that we did was because it was a single glazed building, nothing else was available when it opened in 1947, I think it was, there or thereabouts. It was a single glazed facade. And we did a study on the amount of energy we would save if we made it double glazing, and would that energy saving pay for the removal and restoration of that facade? And guess what? Energy is so cheap, it remains so cheap today that 25 years of energy saving by going from single glazing to double glazing was not enough to pay for replacing the single glass on this facade with double glass. So you might ask me, so why is it that people put double glazing in buildings? That's entirely to do with regulations. And that's another point that I have to make. There are a lot of free market people that insist that the market will always come up with the right answer. But in the area of energy conservation and energy consumption, the progress has really been made on the back of regulation. Obviously, you have some visionaries that try out experiments and they do things that are not required by regulation to push the envelope. But the bulk of the progress is because the rules change and you are required to do certain things by law. And I'll have an illustration in a minute that actually shows the effect of those regulations. So it is the regulations that make you put double glazing in buildings today. It is not the energy saving. Certainly that holds true in America. It may be less true in Europe, where energy is taxed very highly and is therefore multiple times more expensive than it is in the US. But in the US, it's very difficult to justify energy saving technologies based on payback because energy remains very cheap. So that's one part of the story. The other part of the story is to actually show you a progression of design thinking. So over here you have, another purpose of this image. Over here you have the Empire State Building, which if you look at it, takes what you might call a traditional approach to the design of a facade. It's a defensive facade, it's solid. And because you need a bit of ventilation and light, it has punched windows in it to let that through. And a few years earlier, the Chrysler building would have adopted the same approach. So it's like a solid edifice with punched openings for ventilation and lighting. Also, with the Empire State Building, it was one of the first skyscrapers to actually have a rudimentary air conditioning system. So that's going back to like the 1930s, early 1930s. So by then, air conditioning as a technology had matured to the point where you could put it into large buildings. And so in this building, you actually do have, or you had at that time, it's been renovated since, an early type of air conditioning system, which then obviously starts the cycle of increased energy consumption in buildings. Actually, I should tell you another story about the development of air conditioning in buildings. One of the first buildings to be air conditioned was actually the New York Stock Exchange. And Carrier is credited with being the father of air conditioning. And what he actually did was he took a technology that had previously disrupted the ice trade. So in order to get ice in your drink in New York, in centuries past, you would float down cubes of ice down the Hudson River, store them in insulated warehouses in New York, and then the rich could afford to get bits of that ice somewhat into the summer, delivered for preserving food, for putting in their drinks, etc. So there was an ice trade that meant harvesting, transporting, and storing ice in New York in warehouses. the refrigeration cycle that came about disrupted that, and you could now use electricity. So this all happened towards the end of the 19th century, beginning of the 20th century. You could now use electricity to run a refrigeration cycle and create artificial refrigeration. And the sort of hangover from that period is that in the US still, we haven't moved to metric units. We still measure the capacity of air conditioning equipment, even domestic air conditioning equipment, in tons. And so you can say this is a 5-ton refrigeration machine or a 2-ton air conditioner or whatever. That terminology actually means that a 2-ton air conditioner is capable of producing 2 tons of ice in 24 hours. That's the measure of its capacity. And it's a little scary to think that outside my house here, I have a 5-ton air conditioner, which means that when I turn it on, I'm turning on the capacity to produce 5 tons. 5 tons of ice is a huge amount of ice in 24 hours. And in the middle of summer, that thing runs flat out to keep our house cool. So it just goes to show what we've become accustomed to in terms of the consumption of resources. It's kind of crazy. But then the thought of living in this climate in the middle of summer without air conditioning, it would be pretty intolerable. I could stretch the boundary a little bit. I can maybe live in London without air conditioning, but to live in Princeton, New Jersey without air conditioning would stretch me beyond my limits. But anyway, sorry, that was an aside. In carrying on the work though, so when we did this master plan, by the time you go from the Empire State Building to the Secretariat Building, you now see a completely changed approach to the architecture. You have something which is one of the earliest curtain walls on that building, and it is fully glazed except for the lower part spandrel, which hides the air conditioning equipment that cools the space. The rest of it is all clear single glazing. And the 2 facades face due east and due west. And basically the approach of the architects was that, okay, we have this new technology, we have energy, we're going to use energy and technology to liberate our architecture and allow us to put all this glass on this facade. And yeah, the building will overheat, but we have a system that will keep the occupants cool, so we don't care about that. And the result of that kind of thinking, it wasn't bad design, because everything was designed very well. In fact, the air conditioning system was designed very well in engineering terms, but the thinking did not include the conservation of energy or resources at that time, back in 1947. And so in fact, when we looked at the historical records of energy consumption in this entire campus, it was maybe 5 times on a square meter basis compared to a typical reasonably energy efficient building that you would build today. So huge energy hogs as a result of design decisions, but ones that were taken at a time when energy wasn't an issue. Another demonstration of energy not being an issue, these vertical walls that you see on the north and south facades were made of travertine, which is a marble that has all these fissures in it. And the architects did not want that marble to be degraded over time as a result of freeze-thaw action with water getting into the fissures, freezing, expanding, and spalling off bits of the marble. And so the solution to it was to put a steam-heated coil behind each of those facades, 36-story high steam-heated coil. And whenever there was any risk of the temperature outside dropping below freezing, you turn these things on and you have 2 toasty radiators that start radiating to the rest of Manhattan. Crazy if you think about it today. We would never dream of doing such a thing. But at that time, that was a technical solution to an architectural problem. And the fact that it would consume lots of energy, nobody thought about it because energy was so cheap at that time, and nobody was aware of any kind of environmental consequences to the consumption of that energy. Another part of the thinking then, they didn't want cooling towers to sort of obscure the any part or mar any part of this facility with clouds of steam. And they had the East River right there. So they said, okay, when we want to get rid of the heat from this building in the summer, what do? Let's have a couple of large pipes. And so there are two-foot diameter pipes that go into the East River, where they take water from the East River, they filter it, they reject the heat from the building into that water, and they send it back into the East River, which from an energy standpoint actually is quite an efficient way of getting rid of heat from a building. The only problem is it wreaks havoc with the marine life in the water over there. So again, it was very advanced and very clever thinking, but not taking into account environmental impacts, because those impacts were really not part of the public consciousness at that time. It wasn't until the 1960s and the Nixon administration that there began to come this kind of awareness that human activity could, in fact, impact the broader environment and wildlife and all of that. And it started off with pesticides, actually, as the means that started driving that. And so the EPA was actually formed as part of the Nixon administration, and the celebration of Earth Day and all of that, that came about at that time due to that broadening awareness. But even then, there wasn't that much of an awareness of energy as a limiting factor, or the emissions from energy and climate change. They were really not part of the conversation. So coming back to this campus here, over to the right-hand side of the Secretariat building, you see this building by Roche Dinkeloo, which is One UN Plaza, I believe is the name of that building. Now, compared to the Secretariat building, which had nice clear glass, this building came into being after the 1970s energy crisis, where saving energy became the name of the game. And one of the immediate responses to that all over the world, and you see these buildings in many cities, was to clad the building in dark glass. In this case, it was dark glass. In the cases of other buildings, including one that was near our office in London, it was highly reflective mirror glass. So the idea being that, okay, we now can't live without air conditioning, but air conditioning loads are driven very much by solar heat that comes through the facade. So why don't we stop that by making this glazing really dark or really reflective to reduce the amount of heat that comes through? Of course, in reducing the heat that comes through, you're also reducing the light that comes through. And for a short time, Arup in London was leasing a building that had such a dark glass facade. And I can tell you from personal experience, it was horrible working in there, because you could go in on a bright sunny day, get to your desk, look out of the window, and it would look like a grim overcast day outside. So you had no real sense of what was going on outside. Yes, you could see cars and people and so on, but the quality of light was just very poor. And in fact, buildings of that era have a number of problems. One was that kind of factor where it actually created a poor environment. In fact, we were told when we were doing this survey that there's a waiting list of people that would like to relocate from the Roche Dinkeloo building into the Secretariat building, just because of the quality of light and environment that they felt there. But anyway, that's a different story. The other thing that was happening to address the issues of the energy crisis was to cut down on the amount of ventilation air that would go into a building. So research had shown that you only needed about 5 liters per second per person to maintain breathing and other bodily functions. And so a lot of people started designing these buildings with reduced quantities of fresh air ventilation. At the same time, though, what was happening in terms of interior design is that the interior designers were bringing a lot of artificial man-made materials into the workplace in terms of paints, laminates, treatments to wood. The formaldehyde was used as a preservative in a lot of wood products. There were a lot of plastics that were there as part of, if not the furniture, the bits and pieces that people carried around with them. And all of these materials at that time were, these man-made materials would off-gas volatile organic compounds into the environment. Again, it was not perceived as a problem. But what would happen is that a certain percentage of the population, as much as a quarter to a third of people, were actually sensitive to in some ways to high concentrations of these volatile organic compounds in the indoor environment. And so the combination of reducing the amount of fresh air and increasing the amount of off-gassing from these products led to a lot of people feeling pretty unwell in the office environment. And there was the arrival of this thing called sick building syndrome. Initially, when the complaints started, it was ubiquitous. It wasn't just one or two buildings. A lot of modern buildings had people complaining that they didn't feel well. Nobody knew what it was. In fact, one of the projects I was given was to research all of the different things that people claimed might be a reason for sick building syndrome. And I put together a little report with about 10 different things. And in fact, I missed the thing that eventually turned out to be the problem, which was this chemical soup that people would walk into. Poor indoor air quality as a result of off-gassing from the materials that were being used inside. And then one of the things that gave it away was this Monday morning syndrome. Now, we all feel pretty bad on a Monday morning, but the people that were feeling sick would feel sicker on a Monday morning than they felt at any other time in the week. And the explanation for that turned out to be that to save energy, the air conditioning system would be turned off at 6 o'clock on a Friday, and it wouldn't be turned on again until about 8 o'clock on a Monday morning. So over the weekend, these materials that were off-gassing inside the office space would continue to off-gas, but there would be no ventilation to actually dilute the products of that were in the environment. And so the concentration would go up over the weekend and would reach its peak just at the point where you turned on the air conditioning again on a Monday morning. And so that Monday morning effect was a dramatic, measurable impact of the same phenomenon that caused sick building syndrome. Anyway, eventually that was all figured out. And the response today is that the fresh air quantities that we supply are roughly double the minimums that were used then. So we put in about 10 liters per second of fresh air into office spaces. And also there's an awareness of VOCs, or volatile organic compounds. And you can actually specify that the paints and the finishes and the fixtures and furniture and so on have a low VOC finishes. And so it's less of a problem now. So interestingly enough, an approach to reducing energy consumption today might be to re-explore whether we can reduce fresh air quantities, because the amount of pollution that happens indoors is less than it once was, and than it was at the time when those regulations were established. But because it's a little bit of a hot potato, nobody really touches that much or suggests it at this point in time. The closest people have got to is carbon dioxide based ventilation, where you measure the level of carbon dioxide in the indoor environment and you adjust the amount of fresh air to ensure that that remains below a threshold, usually about 600 parts per million. Okay. Sorry, that was a bit of a long. How are we doing, Dan? Can I have some feedback? Is this okay? Do you want me to go quicker, slower?
No, it's up to you, Mahadev. Thank you. You arrived now at Stephen Hall, so please carry on. I see your energy is the same. So.
Okay, so if I'm not boring everyone to death, then I will carry on. Thank you.
No, certainly not me. I don't know. It's not about boredom, but people are usually, I see we had more people, few left, but I think the presentation is becoming, it has the same excitement even for me. So.
Okay, good. Thank you for that.
You see, there is another feedback here from the audience. Great. I'm really interested in this.
Oh, okay, good. I can't see that at the moment, the chat, but that's good to get that feedback. All right, thank you.
Another one, it's really an eye opener. So there are very positive reactions.
Oh wow, okay, that gives me even more energy. Let me carry on. So let us jump now to the
10 hours more with you.
Okay, I wouldn't have the energy for that, but I'm happy to carry on for maybe one more hour. Okay. Let's see how it goes, and if the questions take us into more time, that's fine too. So this is a building for MIT. It's a student residence. When you look at the photograph on the top right, you get a kind of a distorted view of scale, because typically one reads each of those lines of windows as a story. And actually, it is not the case, because every floor has 3 levels of windows. There's a level near the floor, there's a middle level of windows, and then there's a level near the ceiling. So each group of 3 actually is a story, but because that's not articulated on the facade, it looks sometimes in pictures like a much bigger building than it really is. So this is a student residence. It was a subject of an architectural competition, which Stephen Hall won. And the issue with it was that long before we actually got engaged in deciding the details of the design, there were a lot of things being said by both Stephen Hall and the president of MIT about what this building would do. So they were calling it a low energy building. They were saying that it would be only naturally ventilated and there'd be no air conditioning. And it would set new standards in that way for environment, etc. So a lot of tall talk, which is not based on science, because the problem is that if you look at the Boston climate, really it is very difficult to have a building there that's habitable in the summer months without air conditioning. You can maybe just about manage it from September through to maybe the end of May. But June, July, and August, forget about it. Living here without air conditioning would be putting the students through torture. So, but we were presented that as this is what you have to achieve. And it was, if you like, a little bit of an impossible mission. At the same time, elsewhere within the client, you had the facilities people who were well aware that these student dormitories are used in the summertime by conference attendees. So they have conferences at MIT and they use this accommodation to house those people. And they knew that those people definitely would not take kindly to being hot and sticky inside an unair conditioned dorm. So that's where we started off. And so our first approach with this was to figure out how we could minimize the conditions in the summer, to minimize the heat gain going in the summer, and also maximize the effectiveness of the natural ventilation. And this facade that we have here actually was the result of that type of consideration, as well as the structural engineer Guy Nordenson trying to figure out an elegant way of holding the building up and creating a facade at the same time out of that structural element. So this is actually a structural facade. Its quality is very high because it's made of precast elements, which you can actually control very well in the factory and then come and install them on site. And then the decision to put the glazing on the back face of the structure rather than on the front face means that each of these windows is inset by about 20 to 30 centimeters. And so there's a little shading device around each one of the windows. And you can see that with the image on the left, that the windows are actually, the plane of the windows is actually behind the plane of the facade. And just by doing that and reducing the vertical scale of each of these windows, actually this building ended up being very significantly self-shading. So even though you could get direct sun on these windows at certain times of the day, if you look at it as a totality, the building was very well shaded just by making that simple move of reducing the vertical scale of the windows and moving the plane of the glass to the back of the structure, just about a foot, less than a foot, in fact. So that was one move. The other thing is, by having these 3 levels of windows, you could have multiple methods for controlling ventilation. So on a very still day, for example, you could open a window near the floor and a window near the ceiling, and just the natural buoyancy forces would generate a circulation where air would come in at the bottom and go out at the top and get rid of some of the heat that was being generated inside the space. And then within the space as well, exposing the thermal mass. So you see on the bottom right, one of the spaces, not the rooms, this was one of the communal spaces where there's quite a lot of exposed concrete. Aesthetically, that is not everyone's cup of tea, but thermally, it actually works very well. So in a naturally ventilated building, it allows all of the building structure to cool down overnight. And then in the daytime, you can actually close a lot of those windows and reduce the amount of ventilation and rely on the heat absorbing capacity of your building structure to maintain the thermal environment within comfortable levels. So all of that was done in a passive way to control the environment. It then came to the issue of, yes, but Boston is such an extreme climate. You know, if you put this in London, it might have worked without air conditioning. In Boston, chances are it would not. So we had to come up with a system that was not your heavy duty air conditioning with thermostats everywhere and fan assisted units and so on. And we came up with a very simple device. We had reduced the loads to the extent where just a small amount of cold, dehumidified air being supplied into each of the rooms at a constant rate would achieve enough of a trimming of the temperature and humidity to make the space more comfortable for the occupants. So that's essentially what we did. The amount of air supplied to each room matches the amount of exhaust that goes out of the toilet in each room. And so there's a sort of balanced airflow there. And with that type of very simple system, it just kicks in when the outside temperature goes above, I think the set point was 85 degrees Fahrenheit. I don't know what that is in Celsius. It's probably about 23 or something like that. When the outside temperature goes above that, this system kicks in and just sends a small quantity of cold dehumidified air into each room. And that has proved to be sufficient to just take the edge off the summer, put it that way. So it isn't an air-conditioned building in that regard, but it also is because you're using some kind of mechanical means to affect the environment. So it's not a purely natural building. Call it a hybrid building if you like. So we jump to Italy now. Again, this is now a Richard Meyer project. Richard was the winner of a competition that was held by the Vatican. It was a global competition to design a church to commemorate the millennium. And so the project was called Church of the Year 2000. It actually was about 2002, I think, by the time it was finally completed, but it is there and it's a lovely piece of work. And as a piece of spiritual architecture, I like it very much. Of course, there are very many metaphors, if that's the right term, for aspects of the Christian faith with these three shells that are supposed to represent the Father, the Son, and the Holy Spirit. They don't say which is which, but that's the representation with the three shells. Environmentally, we did a lot of things here because very early on, the client said to us that basically whatever systems we put into this building must A, be very economical in terms of how much they cost to run, and B, must be capable of being operated by the parish priest without too much training. So they said, keep it simple, keep it cheap, but it's got to be effective. So that's what we took as our mission for this. The heating was easy enough because we have a floor. All the occupants are mostly down there near the floor. And so by putting in a radiant heating system in the floor, that was quite simple. Circulate hot water through it in the winter time with a small gas boiler. And of course, Rome doesn't get that cold. So it's only under the extreme winter conditions that you even need to turn the system on. And so that solved the heating side. The cooling and ventilation, we were a little more adventurous with it. So you look at these three concrete shells that form the main part of the building, they actually end up having a significant foundation, which is 1 story down. And so below the main level of the church, in the basement, you have these caverns, catacomb-like things, which are going around all of these foundations, which are massive pieces of concrete. So we thought, well, okay, that gives you some thermal mass, which has some real connection with the Earth. And the Earth always maintains a temperature that's somewhere between your daytime maximum and nighttime minimum 3 months ago. So if you're in the middle of August and you go down to the level of this basement, the temperature there, you'd expect it to be the average temperature in maybe May, right? So this is one of these interesting factors as to why some of these very heavy stone cathedrals and so on are much more comfortable inside, even without any systems, than many modern buildings. It's because of the effect of this thermal mass that gives you a month-long or 3-month-long, in some cases, lag in temperature. Anyway, so we thought that we could leverage that that effect, and so over on this side is a courtyard, which is actually a sunken courtyard, so it's a level below the street level. And we said, why don't we provide some air intakes in that courtyard, which is also has a lot of vegetation, so it's a shaded, nice, cool, pleasant courtyard. It's a private one, so it's for use by the clergy, not for the public, except during certain events, I would assume. And the idea was that the air would be taken in there. It would flow through the undercroft of this building, through the basement, through shafts, and then be discharged into this cavern that was underneath the shells, where the foundations were, which would be cool relative to the temperature outside. They would always be at a lower temperature. And then from there, that air would go into the church through slots in the floor. So that was the design. Now that's all very well, but how do you get this air to move? We didn't really want to put in big fans to drive the air movement. And so we decided to make use of this skylight at the top of the church. So by providing operable panels in the skylight that could be adjusted for different levels of opening, when you open the skylight, the warm air at the top of the church escapes to the outside, and it naturally draws the cool air through this sequence of spaces and up from the foundation into the church. Now, it seems to work pretty well. I happened to visit. I visited it only once after it was built, and it was in August, and it was a hot day, and it was quite pleasant inside the church. So I'm assuming it is working as intended. So it's an interesting project because yes, it's for the Catholic Church, but they picked a Jewish architect, Richard Meyer. The two structural engineers that were key to this, Guy Nordenson at that time was a Buddhist, Leo Argyris was Greek Orthodox, their junior structural engineer was a Muslim. I'm a Hindu as the mechanical engineer. And the only Catholic on the team, as far as I could remember, was Ray Quinn, who was my number 2 in doing the mechanical systems. In fact, he did much of the heavy lifting on this project. So that was a very, very interesting backstory to this church that was put in place to celebrate the millennium. And it's something that I feel is a very enlightened approach taken by the Vatican for picking a team to do this very significant project for them. They don't highlight this fact in any of their publicity, but I'm sharing it with you because I know the history of it. Also, during the fee negotiations for this, I had to go over there and speak to the person from the Vatican that was nominated to sort of manage the project. His name was Monsignor Amicarelli, a very understated looking gentleman, but when it came to money matters, he was totally sharp. And I didn't speak Italian, he didn't speak English, and we had to somehow do a fee negotiation. And so we had as a translator a Canadian-Italian architect who spoke both Italian and English. He was sitting there as an interpreter. And we had this back and forth conversation. I would say it's a very complex project. We have to do all this analysis to make the ventilation work. And we're working at a distance from New York. That has additional costs. And Monsignor was saying, yes, but it's the church. We do a lot of good work. We're a charitable institution. And then at one point in this back and forth, of course, he was making his remarks in Italian. I was making them in English. This Canadian architect burst out laughing when Monsignor Amicarelli said something. And I said, what did he say to you? And he translated to me. He said, Monsignor says, don't be so difficult with this negotiation. You'll get your reward in another place. So that was a sort of light point in that conversation. Soon after that, we came to a conclusion and we all left happy. So that was fine. This is just another view of this curved facade. This was actually made by a company called Italcementi that developed a special cement and methodology for precasting these individual concrete blocks, and then to put them in place and post-tension them to actually give you the nice curved shells of precise geometry and quality. So that was a major contribution made by that company, and they donated all of their efforts completely for free as a donation to the church. We were not in a position to do that, given the organization that we are. And on the right here are some of the analysis that we did, again using computational fluid dynamics to show how the temperature would stratify within the space, and how that temperature could be used to generate this suction effect near the floor that would pull the cold air in from the basement space. And then sticking with Richard Meyer, we're now moving to late 90s. This is a courthouse building that the Sandra Day O'Connor Federal Courthouse in Phoenix, Arizona. And I was involved in only one very specific aspect of the engineering here, and that is the air conditioning of the atrium. In fact, this project was started off without any involvement of Arup in it at all. There was Richard Meyer, and he had a local architect in Phoenix, and he had engineering, structural, and mechanical engineering companies in Phoenix that were charged with doing the project. And they developed the design up to schematic design, which in American terminology is about 15% of the way through the project. So it's the early stage scheme design for the project. And it's a stage at which you produce a full set of drawings and outline specification, and you get a cost estimate on the project. So when they did that, they found that everything was fine with the project. In fact, the client loved the design, the internal circulation, the flows, the efficiency, all of that worked out. The one thing was the cost that was a problem. And the element of the cost that was really putting everything over the top was the air conditioning for the atrium in this building. I think I have a picture. Yeah, so this is a picture of that atrium. It's like 100 meters long and 60 meters wide, and it has a special proceedings court inside of it. I apologize for the quality of these photographs. There are some much better quality pictures on the internet that you can look up if you're interested in this project. So this is a very impressive space. It's the main entrance to the courthouse. So the main doors are in the facade that's directly behind us in this view. And you go in and you enter this space, you go through security, and then you go wherever you want within the facility. Everything was good except the conventional air conditioning system that was designed to keep this space cool was ridiculously expensive if you figure it out on a cost per square meter, and also in terms of an energy cost basis. And it's at that point that the Richard Meyer team, a guy called Tom Pfeiffer, who was an architect in his own right, he was the lead architect for Richard Meyer on this project. He called me and he said, look, we have this problem. Do you have any suggestions? So I did have suggestions. And to cut a long story short, after a lot of analyzing the climate and figuring out what would work and so on, the scheme that we came up with was that we would introduce these three openings in the facade. There'd be an air inlet at this point, and two air outlets, one at the top, one at the bottom. I'll explain in a minute what they would do. And in order to make the air through this whole facility move in the way in which we envisioned, we said that underneath this glass roof, you would need to put in a shading device that would intercept all of the direct sunlight hitting that roof or coming through the glass in that roof. It would intercept all of the direct light and only let the diffuse light come down into the lower part of the space. Now, of course, the reason why there was a big air conditioning problem in that atrium was that it was essentially a glass box. It had a glass roof. It had an east-facing facade that was entirely exposed, and a north-facing facade, which in the Phoenix environment in the summer, you get low-angle sun in the north from the northwest and the northeast that actually give you significant heat gains into that space. So to condition the entire volume was really a crazy undertaking. So what we came up with instead was, okay, you put in this shading device. Now our calculation showed that that shading device would absorb so much heat that on most sunny days you could fry an egg on that device. That's how hot it would get. But what it would do is it would heat up the air locally, and that hot air would then be forced to escape out through this vent. Now, as that escape happens, more air has to be sucked in to replace it, and that air sucked in would come in the least path of resistance, which would be this vent that was at the lower level below the shading device. So you have your first air circulation driven by the shading device that happens in that way. Air comes in through this vent, gets heated up by the device, and escapes out through the other end. Now, as that air reaches this back face of the where all of the program spaces are, you have a bunch of balconies, and these balconies also double, they're extra wide, and they double as waiting areas for people that are waiting to do business with either go into a courtroom or visit a lawyer or whatever it is that they do. So these were meant to be occupied spaces. And so as this air comes across, the idea was to spray water into the air. Now in Phoenix, the air is so dry that when you spray water into it, two things happen. The temperature drops and the humidity rises. And as the temperature drops, the air becomes much more dense. So it's heavy relative to the air around it. And so it actually drops under its own weight. So by humidifying the air at this point, you could get this air to drop down to the floor. And that would do two things. Firstly, it would create an air curtain that separates these corridors from the rest of the atrium. And Richard was adamant that he would not have a glass partition between the corridors and the atrium. He wanted it to be open because he felt that that was part of the whole experience of the building. And I completely support him in that. It gave us a lot of challenges, but we found ways of solving those. And this was one of them by creating this air curtain just through natural forces. All you're doing is spraying water into the air. It evaporates and you create this air curtain. What would then happen is that that cooled air would collect in the bottom part of this atrium. And by providing an outlet that was above head height, you could maintain a certain volume of that cool air here. And of course, it would be constantly refreshed by air dropping in from above and air escaping out the front. And this took quite a lot of modeling, analysis, sleepless nights, etc. But we eventually got there with a design that we were confident would work. And by this point, we were at the design development stage of the project, which was about 35% of the way through design. And we handed over our report because our output was in the form of a report and it covered only this part of the building. And the government said to us, "Thank you very much. We'll take it from here." So at the end of the day, it all did work. So this is a picture from the top corridor looking into the atrium. You can see the shading device up at the top. And because it's angled to stop the sun from the south, you still get views from here through to the sky. So if you're standing in any of these corridors and look up towards the shading device, you can see the sky beyond, which is a nice feature. The air comes in, it gets humidified just above this level. And then this cloud that you see here is the water in the process of evaporating. By the time this goes down another story, you can't actually see it because all of the water has evaporated. Now, I don't have time here to tell you the horror story of what the government did with this without our involvement through construction. But eventually we got to inspect what they'd done and solve some of the problems that they'd built into the thing. And I believe it works as intended today. So something that always bothered me about this project was, okay, in order to save the consumption of energy in air conditioning, we were now consuming water, which by definition is a scarce resource in a desert climate. So that is something that bothered me a lot. And I felt that it was a solution to a specific problem that could have been avoided. If you hadn't built a glass box in the desert, you wouldn't have this problem to solve, and you'd end up not consuming either energy or water in order to solve the problem. So it was kind of a self-inflicted wound, I felt, and a bit of an environmental problem. What made me feel better was years later, we did another project in a similar climate in Saudi Arabia. In fact, it's a much drier climate. And the thing in Saudi Arabia is that all of the water that's used in Saudi Arabia by human beings comes from desalination plants. And so you have these desalination plants on the coast, and then the water gets produced, both electricity and water get produced at the coast. The electricity is produced from fossil fuels typically. The water is produced by desalination, and then the water gets pumped inland to wherever it needs to go. So we did a desk study that said, okay, so if you're generating electricity at the coast, you could do two things with that electricity. You take that electricity inland to your site, to this dry environment, and you use conventional air conditioning to produce the cooling that you need. Or you use that electricity at the coast to produce desalinated water, and you pump that water to your site, and you now use evaporative cooling in a similar way to Phoenix, but inside air handling units and so on. You use evaporative cooling to deliver the cooling. Which one of those is more energy efficient? And I checked the calculations I initially did several times, gave them to other colleagues to check, because the results were mind-blowing. By desalinating water and using water for your evaporative cooling, you use less than 10% of the energy that you would use to provide the same cooling using electricity and conventional air conditioning. So obviously that's a technique that will only work in a very dry environment, but it opens up all sorts of possibilities for these desert environments where you can actually use the water for bathing and other things as usual, collect the wastewater, purify the wastewater, and use that gray water, as it were, in an evaporative cooling cycle to do your air conditioning, and you could save oodles of energy. It would be much better for the environment. We presented all of that to the client. They didn't give us the job, but it remains an area of research that I'm interested in, and I hope others, if they have the opportunity to work in these very dry environments, will consider such a scheme, because I think it's something that has a lot of promise for the future. Oh, I'm going backwards, sorry. Okay, so then we come to the issue of the day, which is really carbon emissions. In 2015, there was a landmark move where the majority of countries around the world signed the Paris Accord. President Trump threatened to take the US out of the accord, but I think Biden was elected just in time to stop that process. So the US is still part of the climate accord, which is very important. This is the first time that there's been concerted action around the world where the majority of countries sign up to do something about carbon emissions and do something about their own emissions and reduce them in some way. The problem arises when you say, well, what do we do next? Because the climate accord has set some targets in terms of temperature rise. So they've said that we need to reduce our emissions to a point where the temperature goes up by no more than 2 degrees Celsius. And if possible, it would be better for the planet if we could limit it to 1.5 degrees Celsius. That's what it says in the Paris Accord. It's left to individual countries and industries and so on to figure out what that actually means to them in their practice and what they do day to day, and in terms of local legislation around the countries. So even before then, back in 2007, I was concerned about this because people have been talking about carbon reduction targets for a while. And whereas they can articulate the endpoint, they very rarely articulate the methodology as to how we get there. So I thought, well, why don't I look at the United States and see if I can come up with any kind of guidance on what we need to do. So the first thing to do is, okay, if you want to have reach a particular carbon target by 2050, has anybody done any work on this and plotted out a pathway to get to that? the closest thing I could find was the city of Seattle. So the city of Seattle basically had not only a final endpoint target, this says 2045, but their target was, I believe, for 2050. But they also showed a trajectory of how they would adjust their policies and practices to follow a line of reducing impact to actually get to their endpoint by 2050. And so, of course, closer in time, they had some immediate targets, and then there were periods of time when basically it was a trend that they articulated. So in red here, you see what Seattle was planning to do. So I said, well, okay, that seems to be well thought out for Seattle. What happens if we apply that same trajectory to the entire nation? So that's what is actually shown in terms of millions of metric tons here. This was the total emission from the US, just shy of 2,400 million metric tons of CO2 per year in 2007. And if you applied the Seattle profile to it, this is what the US would have to do to get to this endpoint. Now, we're talking here of just commercial and residential buildings. So this is just emissions from buildings. It doesn't include transportation. It doesn't include industrial activity. And most of the emissions from residential and commercial buildings is to do with controlling the internal environment. That's where we use most of our energy. At least half of it is for that. So one thing is, if you look at the building stock, actually the rate of change of buildings if you take the total population of buildings year on year, that the amount of change is only about 1 or 2%. So I calculated that if you project forward to 2050, 70% of the buildings that you see today, I guess that was in 2007, so some of those have already gone away, but a good proportion of the buildings, say 2/3 of the buildings that you see around you today, would still exist in the year 2050. And so if you didn't do anything about those buildings, the emissions from those buildings would just by themselves far outweigh your targets. So the first conclusion from this analysis is, boy, we have to do something about existing buildings to significantly reduce their emissions. Otherwise, all of these targets that are being talked about in Paris and so on are, we don't have a hope of getting to that point. So that was the first conclusion. Then looking further, the population in the US is projected to grow to, I believe it's 450 million people. It's now about 330 million to 450 million people by the time you get to 2050. It's a projection, but there are multiple sources that quote that number. So then those people need space to live. And it turns out that if they occupy space at the same rate as we occupy space now, you can prorata the building stock to population, and you get to a point where you go out to 2050, and about half of the buildings that you see around you in 2050 are buildings that are there today, and the other half are buildings that we've now built from today onwards, put it that way. So that gives us two opportunities. We could decide today that the buildings that we start building from now on have a much better level of performance than the current building codes and energy codes require of us. In fact, why don't we try and make them net zero? That would be ideal. But in a minute, I'll explain why that's not entirely realistic. And then the other half of the building stock is existing buildings today that we need to somehow renovate in order to improve their performance. So looking at the renovation side, there's work that's been done by the UN and others that suggests that to do renovations to reduce energy typically gets you to a point where you can halve the energy consumption of a building. So on average, take any building, if you set about renovating it to reduce its energy consumption, you can chop about 50% off without it become ridiculously expensive, where it would be cheaper to actually break the building, knock it down, and build something afresh. So that's the decision you have to make. So I said, okay, if the emissions from existing buildings are at this level, the 1636 number on here, we could, by 2050, work on those buildings to cut the emissions down to half. And that represents this bottom part of this bar, the third bar in this graph. I hope you can see the arrow that I'm using to point. This upper part is all the new buildings. So if the new buildings were built to the same standard as today, this is what they would consume. It's not realistic to assume they will all be net zero, because in that building stock are a whole bunch of buildings like labs, hospitals, and other facilities that actually it's very difficult to make them net zero just based on their site. So I'm saying that maybe those buildings consume 15% of what they would as conventional buildings today. So I'm taking all of these emissions, taking 15% of that and getting a total. So if you look at the emissions in 2050, you have the emissions from existing buildings that represent about 80% of the emissions, and we've done the best we can with reducing their emissions. And there's emissions from new buildings, which is about 20% of the total. And there we've done our best to make them net zero or get as close as we can. The difficulty is if you then compare the total that we have with where we need to be in terms of the targets being talked about by Seattle and others, we're still way off. So whereas we need to be at about 350 million metric tons of emissions, we would actually end up at 713 million metric tons. Sorry, there'd be a gap of 713. We'd end up at about 1,000. So that's actually quite disheartening in one way. It's like we worked really hard. We're making some assumptions that are not yet playing out in reality. There are a lot of buildings in design today that are not even aiming to be net zero, let alone net positive. And there's very little activity at aggressively taking the existing building stock and renovating it just for the purpose of reducing energy consumption and so on. So that's the bad news part of it, that we could work very, very, very hard and still not quite get to the target. But the good news part is that we can look at what this represents. And this is where increasing the amount of clean energy generally in the grid will start making a difference. So, for example, if overnight all of the energy in the grid was decarbonized, you wouldn't even have to worry that much about reducing energy consumption in existing buildings, because if you electrify them and use clean electricity, automatically you're reducing carbon emissions. So a big part of this story is that it needs concerted action by building professionals to make sure that all the work that we do aims towards minimum energy consumption, and that work can't just be focused on new buildings, it has to be on existing buildings as well. But in order to get to our endpoint, we also need to have a huge amount of renewable energy supply that comes on stream to compensate for what we can't achieve just through better design in our buildings. And I'm not aware of others that have articulated this, but I think the message is actually getting out there. So I may be wrong. Others may have picked up on this or independently come up with the same conclusions. But there's a lot of work for all of us to do and a lot of encouragement for renewable energy in the grid that we have to really get behind. Now, talking about regulations, I said I would address those. So this is a history of per capita energy consumption in California versus the United States as a whole. And over time, you can see that up to about the early 70s, California and the rest of the US were on a similar trajectory. And then they take a very different course, because in the mid 70s, California put in place some very aggressive energy consumption standards. And they actually started to monitor these. So they actually have Title 24, I think, is the law that actually governs energy consumption in buildings. And there's an aggressive enforcement strategy. So you have to submit your drawings to a bunch of government officials who are qualified, who then look through it and make sure that you've met all of the energy requirements in the code. Now you compare that with New York, that also has an energy code, But here it's all self-certification. So the professional signing it says, yes, this meets the energy code, and then you're done. And also California ramped up their requirements year on year, and they've pretty much managed to keep a static per capita energy consumption all those years from 1970 through to the present. It hasn't gone up. Whereas in the rest of the country, there's been a steady rise, even if we have greater awareness and so on of energy consumption and energy conservation, the laws haven't kept up, and therefore the industry hasn't kept up. Because in most cases, clients are unwilling to put in any kind of investment into their building that raises the capital cost. And unless you can demonstrate a payback in a very short period of time, like 3 to 5 years, they won't pay for measures that will pay back for themselves. And it's very difficult to get things to pay back in a short space of time. I have solar panels on my roof, and at the time when I put them up, which was 10 years ago, there was a New Jersey incentive to defray some of the capital cost. I could get a tax break from the federal government. So I made use of all of that. And then I could sell the clean energy to the state, and I could sell carbon credits through another system. So I got the revenue from that. Even with all of that help, it took me 10 years to pay back the initial investment. If I'd had no help, then that investment would probably pay back in 20 years, 20 to 25 years. Fortunately, all of that has improved. So the panels have got more efficient, they've got cheaper. And so today, with the same area of panel, I could put something up for half the cost maybe and get a payback in less time, even without incentives. But still, it's difficult. If a client puts on you a 3 to 5 year payback period, there are very few things you can do beyond what is mandated by codes to actually achieve better performance. The situation is much better in Europe, where energy is more expensive, and so all of these payback calculations tend to work out more favorably, and therefore more is actually done in buildings in Europe. Okay, so I'm not going to talk about some buildings that I wasn't personally involved in, but they actually demonstrate some features that are relevant to this conversation. So we all walk around with smartphones, and we're all very happy that we can use Zoom, which involves the cloud, and we can store all of our data on Dropbox or iCloud or wherever it is, and access it from wherever we are. And we might be living a very low carbon life because, hey, this tiny device in our pocket, we plug it in and it uses hardly any electricity, and they get more efficient every year. But what we fail to appreciate perhaps is that there's a massive infrastructure, cloud infrastructure, server infrastructure behind all of that that makes it function. And there's one estimate that says that as much as 2% of all the electricity that's used in the world, that includes all processes, including all the industrial processes that are heavy on electricity use and so on, 2% actually goes into data centers. And so looking at data centers as a means of greening them, putting them on renewable energy, and reducing their energy consumption by whatever means is actually a big area of important research and practice right now. And this is one of the first data centers, the Citibank data center in Frankfurt, Germany, where they actually set out with the goals of minimizing energy consumption. And this achieved LEED Platinum as one of its accolades, which was actually a good thing. Then there's work all over the world. This is a zero carbon building in Hong Kong, where you see a sort of sloping roof that's entirely made of PVs, and it generates as much energy in a year as it consumes. This is a government office in the United Kingdom, where the government specified that they would that the building has to be net zero. And so here, this is a model shot rather than a completed construction, but it was built with a lot of photovoltaics, and PVs on these kinds of buildings become the standard way of actually generating your renewable energy on site to meet your demands. However, the issue with that is that you can't always guarantee that the sun will be shining when you need to use the electricity. In fact, it's guaranteed that when you turn the lights on in the evening, you're not generating any energy from your solar panels. So it is typical in these net zero buildings to link them up to the grid, where when you're generating surplus energy in the middle of the day, you send the surplus into the grid to offset the energy that needs to be produced by conventional power stations. And then at nighttime, when you are not generating enough energy, you draw from the grid, and the grid has to turn on all these conventional power stations to meet the demand. And today, when that kind of intermittent renewable energy represents only maybe 15 or 20% of the grid, it's feasible. That actually works. But if we were actually envisioning a grid that goes to 70, 80, 90, even 100% renewable, and you have the intermittency of solar and wind, it becomes a real problem to deal with that. And this is why energy storage is something that is becoming a really big deal right now. And some of the first grid scale battery installations were put in Australia, and there are others planned in other places. So big scale battery installations, and Tesla is working very much in that arena. That is one solution. There are other battery technologies where there are actually flow batteries that use the flow of an electrolyte through a sort of industrial process to store the energy. That's another. There's a more traditional means of storage, which is called pumped storage. So with a dam, with a hydroelectric dam, what you do is that you release water at the top, it flows through a turbine and generator, generates electricity on the way, and then flows out at the bottom. If you create a lake at the bottom as well, then when you have surplus electricity in the middle of the day, you can pump the water back up to the top of the dam. And then when you need that electricity, you let it flow back down under gravity through your turbines. So that's a pumped storage scheme. Those actually exist in many parts of the world already. The problem with any of these storage schemes is that there are losses. So the energy you get back out of it, having stored it, is 2/3 to a half of the energy that you put in. So, but that's okay if you have a lot of solar or wind energy available to you. You can do that and still have an economical way of doing things. Another form of storage that's being talked about now is hydrogen, where if you apply an electric current to water, the water breaks down into hydrogen and oxygen. You can release the oxygen into the environment, which is a good thing. It refreshes the oxygen in the environment, and you can capture the hydrogen as a fuel source. And there are now hydrogen-powered vehicles. They're more concept vehicles. Toyota has one, and so on. I don't know if they're broadly available, although I did see a hydrogen Hummer traveling around in Los Angeles, of all places, a number of years ago. So clearly, you can if you have access to a supply of hydrogen, you can convert an internal combustion engine to run on hydrogen. It is possible, but it only makes sense if the hydrogen is coming from electrolysis of water. In other words, from a renewable source. At the moment, 80%, I think it is, of commercial hydrogen that you can buy comes from natural gas, and therefore it actually is based on a fossil fuel, and using that kind of hydrogen doesn't do you much good, environmentally speaking. But as electrolysis takes off, hydrogen might become an important part of the renewable energy economy. And then it's a storage device where you can store the hydrogen theoretically indefinitely. It doesn't degrade with time. And so you get over this intermittency. And then converting the hydrogen back to electricity can be done by passing it through a device called a fuel cell, where the hydrogen goes in, electricity comes out, and the waste product is just water. So you just drain that away. So hydrogen shows some promise. The other good thing about hydrogen is you can modify most natural gas networks and appliances to run on hydrogen. So there are huge natural gas networks all over the place. I have natural gas coming to my house. It provides the energy for cooking. And if I could switch that to hydrogen, that would be a wonderful thing. It's not yet in place, but maybe within a decade or definitely 2 decades, it could be that you have a choice of hydrogen as a fuel to burn in your home and in your heating system. So regional transit center, again, the reason for showing all these projects is that they're not particularly specialized in terms of architecture. So you can have a net zero building that on the surface might look like any other regular building. There's nothing about it that screams I'm net zero. And so net zero buildings are not an architectural style. Although some of the common features is that somewhere associated with them will be some wind turbines or some solar panels, and they may be more or less visible depending on the particular design. Here they're completely clad. They completely clad the building and come down to ground level, so they're expressed in this particular project, which is a school. I believe this is Raphael Vignoli. And then this is a small project where it forms a solar canopy at the top. And then there are many, many designs that actually express a solar canopy that creates a kind of shading structure right over the entire building and can be used for harvesting water as well. And this building, which is one I was involved in and did the original scheme design and calculations for this, is by Enrique Norten. At the time when this was first built, they ran out of money for the solar panels, but they've since put in the solar panels. So when we designed it, we were expecting the solar panels to generate 62% of the energy required by the building. I believe the new panels are more efficient, and therefore they're probably getting very close to net zero in terms of the electricity consumption, but also water is harvested off these panels, so they're connected to a drainage system. And more than half of the water consumed by this building comes from the stormwater that's collected on the roof. So going on to the future, urbanization is a big theme. And prior to COVID, everyone was thinking, well, actually denser cities is one of the ways in which we can reduce energy consumption. And in fact, if you look at cities like Hong Kong, where the number of private vehicles is limited and there's heavy use of public transportation because it works very reliably and efficiently, the actual carbon footprint of your average Hong Kong citizen is relatively low compared to, say, a typical suburban American. And so people were thinking in terms of highly dense cities with shared facilities and public transportation and so on. Maybe COVID is going to change that. I do not know, because there was a flight from place. Anyone that had an option left cities like New York to go and stay with their parents or wherever else they could, away from the city in a less dense environment. Maybe that's a trend that'll continue, or maybe we'll overcome that and go back to living in dense cities. I do not know. But one feature of dense cities is very tall buildings. And the question is it possible to make a very tall building net zero? In 2020, that answer was no, it's not possible. The technologies weren't there. But I don't want to dwell on this, but we did a study with an architectural firm called Kish & Cathcart, and got a grant, NSF grant, working with Rutgers University as well, to really study that in some detail. And we projected forward, so sorry, that's not the right image. This is the right image. We projected forward to 2050. And by 2050, there are a number of technologies that are actually still in the process of improvement. One of them is LED lighting. There's still a long ways to go in terms of efficiency improvements in LED lighting. And if you project forward to 2050, even though they're very efficient today, and most new buildings have only LED lights, it's very rare to find fluorescent lights or any other source specified today. By 2050, they will become even more efficient than the ones that are there today. Also, clever facade materials that themselves can generate a certain amount of electricity as the light passes through the glass. Today, they're not widely used because they're expensive, and also there's a kind of yellowish color that they give to the glass. But the sense is that many of those problems can be solved, and you can get to a window that still has a good level of light transmission, maybe 60% or better, and will still generate a little bit of electricity as the light comes through. Those are all on the cards. There are advances in HVAC systems where a greater appreciation that radiant-based systems are making use of some clever properties of certain types of plastics can actually allow us to be comfortable in environments that traditionally we would consider to be uncomfortable. Because by creating a radiant source of cooling, you become more tolerant of higher air temperature and particularly higher humidity, which is interesting research that's being done by my colleague Forrest Meggers at Princeton University. And he's been publishing papers on that in recent times. And he built a pavilion in Singapore that actually demonstrated the effect. And people were stunned that they were essentially outside and they walk into this covered area and suddenly they're feeling comfortable, when in fact the temperature and humidity are still the same as they would be outside. So there are those kinds of advances, and taking all of that into account, the long and the short of it in terms of this particular project, the 2050 tower, was that we showed that you could achieve energy autonomy in terms of generating as much energy as you consume in something like in a tall tower like this. It was close, so getting to a positive net positive building where you're generating more energy than you're consuming would be difficult in a tall tower. But in something like a house or a one-story building or even a two-story building, making those net positive is actually quite easy in most climatic zones around the Earth. Yeah, this is just more of the work that was done comparing 2020 and 2050. And in order to do the energy analysis of this building, we actually surrounded it in our energy and visual models with other tall buildings from around the world, so that there were some shadows and things cast on the facade throughout the day. So it was somewhat theoretical, but also we tried to make it as realistic as possible as a study. And we also put in some modules for growing food and dealing with waste and so on. So although we have some heavy challenges ahead of us in terms of reducing the carbon intensity in our economies and so on, the good news is that one of the problems we don't have is a shortage of renewable energy. Now, there was a time when I think it was the nuclear industry and the petroleum industry were both sort of touting the kind of, oh, there's limited wind power, there's limited solar, you can't get it all. So don't sort of hang your hat on renewables. I say that that's complete rubbish. This is a study that was done by Frank Mierlo a number of years ago. And I actually went back and recalculated some of these numbers. I didn't get exactly the same numbers as him, but they're close enough. So I'm using his numbers here. He said that if you look at the continuous energy consumption of all of humanity at the moment, it is something like 15 terawatts of energy constantly being consumed. Now, it's important to realize that only about 1/3 of humanity, and that probably includes everybody on this call, or most people on this call, has complete access to energy. I turn the switch on at night to turn the lights on, and I have zero doubt that the lights are going to come on. I can be absolutely sure that my air conditioning is going to work. I can be totally sure that I'm going to get a gas supply to cook my meal. So I have an abundant and reliable source of energy to me, and about 1/3 of humanity falls in that same category. There's another 1/3 of humanity that only has intermittent access to energy. They turn the lights on and they may or may not get a light. They have power cuts, they have intermittent supplies. Maybe they have to get cylinders which to supply gas, which can be in a shortage situation. So they have intermittent access. And there's a full 1/3 of humanity that doesn't rely on modern sources of energy at all. They live in a subsistence agricultural environments. They're still using firewood and charcoal and things like cow dung as fuel sources. Maybe a little bit of electricity has come in, but there are many parts of India, for example, that are not electrified. And so about 1/3 of humanity across the world does not have really any access, and therefore is not making any impact to either energy consumption or to carbon emissions. across the world. Very, very little impact. So let's envision a future where all humanity, everybody around the world, actually does have that good level of access to energy. Plus, we have a population that's going to grow from where we are now to a projected peak of somewhere around 10 billion or maybe even 11 billion. And we are currently at somewhere between 7 and 8 billion in terms of human population. So population growth plus better access for everyone to energy will obviously take this consumption number and increase it. But what will it get to? My estimate is that it'll get to about 3 times this number. It'll get to about 45 terawatts. Maybe 50, but 45 was the number that I came up with. Now, if you compare that 45 terawatts with the availability of wind, 370 terawatts, it's only 15%. So if we were to harness only 15% of the wind energy that's available, you could meet all of humanity's needs. And with solar, it's even more extreme. So you just need a tiny fraction of the solar energy. Now, of course, you can't collect solar energy in the middle of the ocean, and this number represents all of the solar energy that comes. But because it's such a tiny fraction, I have no doubt whatsoever that there is plenty of renewable energy out there to satisfy all of humanity's needs and keep us all going to a very high standard of life. So it's not that we have to become cave people in order to solve our carbon emissions problems. We can actually do it with the technology that we have. But it will take investment, it'll take policy change, and it'll take development in energy storage is one of the key technologies that has to actually get much better before we can go to 100% renewable society. Thank you.